Here's a typical problem. If a field has an area of 55 units, and one side is 6 units longer than the other, how long is the shorter side? The Babylonian solution was to reconfigure the field as a square. Cut 3 units off the end, and move this round. Now, there's a 3x3 piece missing, so let's add this in. The area of the field has increased by 9 units. This makes the new area 64, so the size of the square are 8 units. The problem solver knows that they've added 3 to this side, so the original length must be 5. It may not look like it, but this is one of the first quadratic equations in history.
In modern mathematics, I would use the symbolic language of algebra to solve this problem. But the amazing feat of the Babylonians is that they were using these geometric games to find the value, without any recourse to symbols or formulas. The Babylonians were enjoying problem solving for its own sake. They were falling in love with mathematics.
The Babylonians' fascination with numbers soon found a place in their leisure time too. They were avid game players. The Babylonians and their descendants have been playing a version of backgammon for over 5,000 years.
So the Babylonians played board games, from very posh board games in royal tombs to little bits of board games found in schools, to board games scratched on the entrances of palaces, so that the guardsmen must have played at times when they were bored. And they used dice to move their counters round. People who played games were using numbers in their leisure time to try and outwit their opponent, doing mental arithmetic very fast. And so they were calculating in their leisure time without even thinking about it as being mathematical hard work.
Now's my chance.
I hadn't played backgammon for ages, but I reckon my maths would be good enough to give me a fighting chance.
Okay. So it's up to you. So 6, and I need to move something, so...
But it wasn't as easy as I thought.
Okay.
Ah, what the hell is that?
Yeah, this is
1, this is 2. Now you're in trouble.
So I can't move anything, can I? I can't move these anyway.
You cannot move these. You can.
I've just got to... Oh, gosh.
Exactly. There you go.
You seem to be...
3 and 4. So.
Just like the ancient Babylonians, my opponents were masters of tactical mathematics.
Yeah. Put it there. All right, good game.
The Babylonians are recognised as one of the first cultures to use symmetrical mathematical shapes to make dice. But there is more heated debate about whether they might also have been the first to discover the secrets of another important shape, the right-angled triangle. We've already seen how the Egyptians used a 3-4-5 right-angled triangle. But what the Babylonians knew about this shape, and others like it, is much more sophisticated. This is the most famous and controversial ancient tablet we have. It's called Plimpton 322. Many mathematicians are convinced it shows the Babylonians could well have known the principle regarding right-angled triangles, that the square on the diagonal is the sum of the squares on the sides, and known it centuries before the Greeks claimed it.
This is a copy of the arguably most famous Babylonian tablet, which is Plimpton 322. And these numbers here reflect the width or height of a triangle, this being the diagonal. The other side would be over here, and the square of this column plus the square of the number in this column equals the square of the diagonal. They are arranged in an order of steadily decreasing angle on a very uniform basis, showing that somebody had a lot of understanding of how the numbers fit together.
Here were 15 perfect Pythagorean triangles, all of whose sides had whole number lengths. It's tempting to think that the Babylonians were the first custodians of Pythagoras' theorem. and it's a conclusion that generations of historians have been seduced by.
But there could be a much simpler explanation for the sets of three numbers which fulfill Pythagoras' theorem.
It's not a systematic explanation of Pythagorean triples. It's simply a mathematics teacher doing some quite complicated calculations, but in order to produce some very simple numbers in order to set his students problems about right-angled triangles. And in that sense, it's about Pythagorean triples, only incidentally.
The most valuable clues to what they understood could lie elsewhere. This small school exercise tablet is nearly 4,000 years old and reveals just what the Babylonians did know about right-angled triangles. It uses the principle of Pythagoras' theorem to find the value of an astounding new number.
Drawn along the diagonal is a really very good approximation to the square root of 2. And so that shows us that it was known and used in school environments. Now, why is this important? It's because the square root of 2 is what we now call an irrational number. That is, if we write it out in decimals or even in sexagesimal places, it doesn't end. The numbers go on forever after the decimal point.
The implications of this calculation are far-reaching. Firstly, it means the Babylonians knew something of Pythagoras' theorem 1,000 years before Pythagoras. Secondly, the fact that they can calculate this number to an accuracy of 4 decimal places shows an amazing arithmetic facility, as well as a passion for mathematical detail.
The Babylonians' mathematical dexterity was astounding, and for nearly 2,000 years they spearheaded intellectual progress in the ancient world. But when their imperial power began to wane, so did their intellectual vigour. By 330 BC, the Greeks had advanced their imperial reach into old Mesopotamia. This is Palmyra in central Syria, a once great city built by the Greeks. The mathematical expertise needed to build structures with such geometric perfection is impressive. Just like the Babylonians before them, the Greeks were passionate about mathematics.
The Greeks were clever colonists. They took the best from the civilizations they invaded to advance their own power and influence. But they were soon making contributions themselves. In my opinion, their greatest innovation was to do with a shift in the mind. What they initiated would influence humanity for centuries. They gave us the power of proof.
Somehow they decided that they had to have a deductive system for their mathematics. And the typical deductive system was to begin with certain axioms which you assume are true. It's as if you assume a certain theorem is true without proving it. And then using logical methods and very careful steps, from these axioms you prove theorems. And then from those theorems you prove more theorems. And it just snowballs that way.
Proof is what gives mathematics its strength. It's the power of proof, which means that the discoveries of the Greeks are as true today as they were 2,000 years ago. I needed to head west into the heart of the old Greek Empire to learn more. For me, Greek mathematics has always been heroic and romantic. I'm on my way to Samos, less than a mile from the Turkish coast. This place has become synonymous with the birth of Greek mathematics, and it's down to the legend of one man.
His name is Pythagoras. The legends that surround his life and work have contributed